Every engineered structure, from the smallest component to the largest bridge, carries a hidden risk. This risk is the potential for fracture. Things break. Sometimes they break with little warning. Understanding why materials fail is not just an academic exercise. It is a fundamental necessity for modern engineering. Without it, we would be designing in the dark, hoping for the best, but unprepared for the worst. History is unfortunately littered with examples of catastrophic failures. The Liberty ships during World War II experienced sudden, brittle fractures. Early de Havilland Comet aircraft tragically broke apart in mid-air. These events were stark reminders of our incomplete understanding of material behavior. They highlighted the devastating consequences of overlooking the potential for cracks to grow and cause failure. These incidents spurred intense research. They drove the development of fracture mechanics as a distinct engineering discipline. Learning from these past failures has made our modern world significantly safer. Fracture mechanics is more than just a post-mortem science. It allows engineers to anticipate how cracks might behave under specific conditions. This proactive approach is essential for engineers in mechanical, civil, aerospace, and materials science fields. So, what exactly is fracture mechanics? At its core, fracture mechanics is the field of study concerned with how cracks initiate and propagate in solid materials. It examines the conditions under which a crack or flaw in a material can grow, potentially leading to complete failure of the component. Traditional methods often assume materials are perfectly uniform and free of defects. Fracture mechanics, however, acknowledges the reality that flaws are almost always present, even if they are microscopic. It provides the tools to assess their impact. The significance of fracture mechanics lies in its ability to provide quantitative answers. It helps us predict the load-bearing capacity of a structure when a crack is present. This is incredibly important for ensuring safety. Imagine an aircraft wing or a pressure vessel. These components may develop small cracks during manufacturing or service. Fracture mechanics allows engineers to determine if these cracks are dangerous. It helps decide if the component needs repair or replacement. This prevents catastrophic failures. It also allows for more efficient use of materials, avoiding overly conservative designs that are heavy and expensive. To understand fracture mechanics, we must first learn its language. A central concept is the crack tip. This is the very front or leading edge of a crack. Stress becomes highly concentrated at the crack tip. The sharper the crack, the higher the stress concentration. This localized region of intense stress is where the material is most vulnerable. The stress intensity factor, K, quantifies the severity of the stress field at the crack tip. It depends on the applied stress, crack size, and component geometry. Every material has an inherent ability to resist crack propagation. This property is called fracture toughness, denoted as Kc or KIC. It represents the critical value of the stress intensity factor before a crack propagates uncontrollably. Section 4. When materials break. Understanding fracture types. Materials do not all break in the same way. One common type is brittle fracture. This type of fracture occurs suddenly and with very little warning. There is minimal plastic deformation before the crack rapidly propagates through the material. Brittle fractures often exhibit a flat, crystalline appearance on the fracture surface. Materials like ceramics, glass, and some metals at low temperatures like steel below its ductile to brittle transition temperature are particularly susceptible to brittle fracture. In contrast to brittle fracture, ductile fracture is characterized by significant plastic deformation before and during crack propagation. Materials that fail in a ductile manner will often show signs of necking or localized thinning near the fracture site. The crack tends to grow more slowly, providing some warning before final failure. Fatigue fracture is a very common failure mechanism. It occurs when a material is subjected to repeated or cyclic loading, even if the maximum stress applied in each cycle is well below the material's yield strength. Creep fracture is a time-dependent failure mode that occurs in materials subjected to sustained stress at elevated temperatures. Section 5. Solving the puzzle. A guide to failure analysis. When a component or structure fails, a thorough failure analysis is essential. This is a systematic investigation aimed at determining the root cause or causes of the failure. The primary goal is not just to understand what happened, but why it happened. This knowledge is crucial for preventing similar failures in the future. A comprehensive failure analysis involves several key steps. each providing valuable pieces of the puzzle to understand the sequence of events leading to breakdown. The first step in any failure analysis is usually a detailed visual inspection of the failed component and the fracture surfaces. This is often done with the naked eye, or with low-power magnification. Macroscopic features can provide immediate clues. Following visual inspection, material testing and microscopy are often employed. Material testing might involve verifying the material's composition through chemical analysis. The final major component of a failure analysis is often stress analysis. Section 6. Fracture Mechanics in Action, Real-World Impact. The principles of fracture mechanics have a profound impact on many industries. The aerospace industry relies on fracture mechanics for aircraft safety. Components like the fuselage and engine parts face complex loads during flight. Fracture mechanics helps design damage-tolerant structures. They can withstand small cracks without catastrophic failure. It dictates inspection intervals to detect and repair growing cracks. In the automotive industry, it ensures durable and safe vehicles. Car components must withstand dynamic loading and environmental conditions. Engineers design components to resist fatigue failure. Pressure vessels and pipelines are critical in chemical plants and oil and gas industries. They contain fluids or gases under high pressure and extreme temperatures. Failures can cause explosions, fires, and environmental damage. Section 7. Building Resilience, Designing for a Safer Future. The ultimate goal of understanding fracture mechanics and failure analysis is to build more resilient and safer engineered systems. It is not enough to simply design a component to be strong enough to carry the expected loads. Engineers must also proactively consider the possibility of flaws and the potential for crack growth. This means designing with failure prevention in mind from the very earliest stages of the design process. One practical design strategy is careful material selection. Engineers must choose materials that possess adequate fracture toughness for the specific application and its operating environment. Another key strategy is to design for inspectability and damage tolerance. Critical areas of a structure, where cracks are most likely to initiate or cause the most harm, should be designed to be accessible for regular inspection. This allows for the early detection of any flaws before they reach a critical size. In conclusion, fracture mechanics and failure analysis are indispensable tools for the modern engineer. Continuous learning and application of these concepts are essential for pushing the boundaries of engineering innovation while safeguarding lives and resources.